Okay, like I just said, yeah, a differential equation is just an equation that has a derivative in it. And like when you solve an equation, like when you solve a regular equation, you're looking for all the x values or whatever values of your variable that make the equation true. Doing the same thing with solving a differential equation, you're looking for all of the functions that satisfy that differential equation. So in order to do it, all we do is we say, all right, put that dx over here and integrate both sides to get y equals something like tangent x plus x squared plus 5x plus our constant, right? We're all good and familiar with this, no issues with that. Right? Just a simple basic integration, right? This is the general solution to this differential equation because we weren't given any specific values. Hold on one second. Okay, sorry about that. Everybody good with that first one, yeah? Okay. All right, what about this one? Now we have an initial condition. We call these initial value problems. We have to find the constant. We have to solve for the constant after we do our integration. Right? So integrate both sides. Y equals e to the x minus 2x cubed plus a constant. And we plug in our value of 1 for x and 0 for y. And get a constant of 2 minus e. Good or no? Any issues there? Easy enough? Should be pretty straightforward. All right, what about this one? When we integrate, we should get y equals what? Yeah, that's right, negative cosine x, right? And then plus x squared plus our constant. And we plug in 0 for x and 3 for y. What do we get for our constant? What do we get for our constant? We get 4. Good. So our function is y equals negative cosine x plus x squared plus 4. Pretty easy, right? And both of these functions were functions that were continuous for all real numbers, which makes this even easier. But we should hopefully remember that sometimes we end up with functions that are not continuous for all real numbers, like this one. And then we have to deal with finding what we call the interval of validity. So we'll talk about that in a second here. So when we integrate this one, we should get y equals x squared over 2 minus tangent x plus a constant. And when y is 3, x is 0. So we get a constant of 3. And we have y equals x squared over 2 minus tangent x plus 3. And how do we determine the interval of validity for this? Who remembers how to do that? Find the discontinuities, right? It says discontinuities at plus or minus pi over 2, 3 pi over 2, and so on, 5 pi over 2, 7 pi over 2, 9 pi over 2. And we then look for our interval of validity by finding the one continuous part of our function that includes the initial condition. So our initial condition was that x is 0, so that ought to fall between negative pi over 2 and positive pi over 2. So we'll say that this is valid for negative pi over 2 to pi over 2. So we need a constant of positive 3 on this specific interval. Anywhere outside of this interval, it doesn't matter what the constant is, as long as it's x squared over 2 minus tangent x plus or minus something. Right, we still get this as our derivative. And as long as on this interval the constant is 3, we still have this as our derivative, and it goes through this point. Good or no? Any questions or issues with that? Yes, Nick, the interval only applies to the function, not the derivative. And Shayla, yeah, the interval of validity will, normally it'll always be in parentheses. I mean, you can't have a value of negative pi over 2 and pi over 2, right? So it's going to be in parentheses because those are the places where we have our discontinuities. So function doesn't exist at those two values. Everybody good there? All right, you guys do this one on your own real quick. I'll give you 1 minute. Ready, go. So we integrated to get a equals natural log absolute value t, and then negative t to the negative 2 became a positive 1 over t plus 6t plus your constant. And when a was 0, t was 1. So our constant was negative 7. And our interval of validity, well, we have a discontinuity here at t equals 0. Right? We know t cannot be 0. T can be negative numbers because of the absolute value around that natural log of, or around the t within the natural log, but we know t can't be 0. So we pick the interval between 0 and infinity because there's no other discontinuities, because that's the one that includes t equals 1. Good or no? All right. Okay, so now we'll do a couple of motion problems, remembering that the integral of velocity is position, and these should be pretty straightforward, I hope. But integral of velocity is position, integral of acceleration is velocity. So you should be able to determine what the position of the particle is at t equals 3, given its position at t equals 2, and the velocity function. All right, so I'll give you guys a minute to do this one on your own. And then we'll go through this and do the next one together probably. Ready, go. So we integrated this to get the position function was equal to 1/2 t to the 4th plus t cubed plus a constant. Is that right? And if t was 2, we should get 1. So 2 to the 4th is 16 over 2 is 8. And we should get c equals negative 15. So our x of t function should be 1/2 t to the 4th plus t cubed minus 15. And x of 3 ought to be 81 halves plus 27 minus 15, or 105 halves. So what y'all got?
Yes.
Perfect. This is all easy stuff, right? Should all be very, very straightforward. Yes, good. Okay, we'll do, I see no reason to do that. Acceleration to velocity, easy enough. All right. Why don't you guys do this one? This one, second order differential equation. We're gonna go from acceleration all the way up to position. So I'll give you 2 minutes. This one might take a little bit more time. 2 minutes to work through this one, and then we'll go through it. Ready, go. All right, so we'll integrate the acceleration to get velocity is t cubed plus t squared over 2 plus t plus our constant. And if t is 2, we should get a velocity of 9. So that'd be 2 cubed is 8. That's a 2, and that's a 2. So we end up with our constant here being -3. So v of t is t cubed plus t squared over 2 plus t minus 3. Is that what everybody got there for that one? For the first part?
Yes.
Okay, and then we'll integrate it again to get our position function, which should now be t to the 4th over 4 plus 2 to the 3rd over 6 plus 2 to the 2nd over 2 minus 3t plus some other constant. We'll call it constant 1. And if we plug in 1, we should get 6. So a 4th plus a 6th plus a half minus 3 plus some other constant. And we ended up with 9 minus a 4th plus a 6th plus a half. So we got 9 minus, what is that, 11/12 if we combine all those together. So I think that comes out to be constant 1 is 97/12. Is that what you got there?
Yes.
Cool. And so x of t would be, the function we had plus 97/12. So I'll just evaluate x of 2. Should be what? This is 16/4 or 4 plus 8/6 plus 2 minus 6 plus that 97/12. So we ended up with what? 8/6 plus 97/12, which would have been what? 113/12. Is that what you all got?
Yes.
All right. Anybody have any issues with that? Wonderful. All right. Simple, basic initial value differential equation problems. Some of them with velocity and acceleration and all that. What about ones like this, where we're given a derivative? Derivative is equal to something like e to the negative x squared. How do we integrate e to the negative x squared? Anybody? Anybody? Nobody? Hopefully nobody. I guess it's nobody, right? The integral of e to the negative x squared doesn't have an explicitly defined integral. There's no function that represents this other than some made up function that we call the Gaussian integral, which is not a real function. I mean, it is a real function in some terms, but it's not an explicitly defined function. We can't write it out in algebraic terms. or even with transcendental functions, with E functions, or with trig functions, or hyperbolic trig functions. There's no nice way to write this out. And so suppose we wanted to find the solution to this where f of 7 is equal to 3. We need to use the fundamental theorem of calculus. And we would say, well, the integral should just be the integral from some constant to x of e to the negative t squared dt plus some other constant. And we have to figure out values of C1 and C2 to make this true. This is our function. The derivative of this function, according to the fundamental theorem of calculus, should be e to the negative x squared, because the derivative of an integral from a constant to x is just the function in terms of x, and the derivative of some constant is just 0. Would you all agree with that?
Yes.
Okay. So constant 1 needs to be what value in order to for us to be able to actually evaluate this integral when we plug in 7 for x? F of 7 looks like this, right? The integral from the constant 7 of e to the negative t squared dt plus that other constant. So what do I need to put down here as my lower limit so that I can actually evaluate this integral without having to approximate it using, the trapezoidal rule or calculator or something? What's the only value I can put down here that makes it possible for me to evaluate this integral? I'm not going to integrate it. I just need to be able to evaluate it. Exactly, Alice. We need that lower limit to be 7. So if constant 1 is 7, then the integral from 7 to 7 of any function is just 0. And if f of 7 is this plus a second constant, and that needs to equal 3, what does the second constant need to be? C2 needs to be, this whole first part is 0, and it needs to equal 3. Constant 2 should be 3. So we would say that f of x is equal to the integral from 7 to x of e to the negative t squared dt plus 3. And suppose I asked you, what was f of 1, let's say. You should be able to figure out what f of 1 is. F of 1 is the integral from 7 to 1 of e to the negative t squared dt plus 3. And your calculator will tell you what that is, right? Rounded to 3 decimals, what should that be? All right, 2.861, is that everybody but Nick seems to agree that it's 2.861? And there are lots of nice, simple functions. I don't forget to add the 3, Nick. There are lots of functions that look like nice, simple functions that we might think are ones that we should be able to integrate, but there are a bunch that you cannot. So just for the heck of it, let's make sure we can do another one of these. I'll give you another function that you can't integrate here. Let's say that dy dx is equal to sine x over x, and y equals 2 when x equals 1. And I want to find out what is the value, what does y equal when x equals 3. So I'll give you a minute here to see if you can work this one out on your calculator and write out the actual function itself. Ready, go. We should have got y equals what? The integral of sine t over t dt. And that integral should have been from what value to x? It should have been from 1 to x, and we should have needed to add what to it? Our y value, right? It should have been plus 2. And so y of 3 should have been the integral from 1 to 3. Sine t over t dt plus 2. And what did that come out to be?
2.903.
2.903? Yeah. People agree with that? Yeah. Good. There's a lot of different functions like this that are just, they don't have, we call them, I think I called them explicitly defined integrals, but also call them elementary integrals. They don't have elementary antiderivatives. So like sine of x over x doesn't have an elementary antiderivative or an explicitly defined one. This one's called, it has a function that's been made up that is used as its integral, but it's not a regular function that we use. It's called the sine integral. And the other one, like I said, is called the Gaussian integral. There's other ones, just to recognize when you might have to use this method. It might be helpful to know some of these off the top of my head here. 1 over ln x is another one. No elementary antiderivative for that one. This one is called the logarithmic integral. Surprise, surprise. What else? There's the elliptical integral. This one doesn't have an elementary antiderivative. So if you see these ones on the AP test, you know you're going to have to use a calculator, but chances are if you saw them, you'd be in the multiple choice section and you'd see a bunch of answer choices that were, decimal approximations, and you would have done it, you would be on the calculator section, so you'd already know. Can't really think of any others off the top of my head. Sine of x squared and cosine of x squared. I know these ones don't. I can't remember the name of what the integral that's been made up to make this integral to be able to integrate this function is, what the function they call it is. It's Fresnel integral, I believe. That sounds right. That might be a different one though. Nah, I think that's this one. Anyway, there's some that you might come across someday that in higher math classes they use these. You can use these different functions to get these integrals, and they're called, like I said, this one's called the sine integral. The first one's the Gaussian integral. This one's the logarithmic integral. This one's the elliptical integral, and I believe that one's called the Fresnel integral. And there's others. There's some other ones that come up fairly common. But yeah, cool, good. Everybody all right with that? Cool. All right, so just recognize how to do this with the calculator. So tonight for your homework, you're going to have some problems where you have to do initial value with the calculator, and some problems where you have to do initial value without the calculator. So just be prepared for both of those. Now let's move into a little bit of a talk on slope fields, right? And hopefully we remember what a slope field is. That a slope field is just a graphical representation of the solution to a differential equation. So our differential equation dy dx equals cosine x, if we were to go in and figure out what dy dx equals at different x values, we could take each of those values, like at x equals 0, what does dy dx equal? Should equal cosine of 0, which is 1. We would just take a small little line segment with a slope. That's what dy dx is, right? It's a slope of the tangent line. of 1, and we'd sketch them all in there. And we could just continue on saying, all right, well, what about when x is pi over 2? dy dx would be 0. And at x equals pi, it would be -1. And at 3 pi over 2, it'd be 0 again. And then back to 1 again at 2 pi. And 0 at -pi over 2. And -1 at -pi. And 0 at -3 over, or -3 pi over 2, and 1 at -2 pi. And we'll note that any value we choose here, let's just choose the origin. If we follow the slopes, right, this goes from 1 to 0, so it's got to narrow out. Then it's going to go from 0 to -1, so it's got to get steeper. Then it's going to go from -1 back to 0. Horrible. And then it's going to go back up to 1. And it's going to do the same thing over here, and it's just going to look like a sine curve, right? That's what's, I just lost it. It's going to look like a sine curve, right? And that's exactly what it should look like, because the solution to this is y equals sine x plus a constant. And the whole reason that this works is the idea of linearization. Right? We're familiar with linearization, right? On a small scale, the tangent line begins to resemble the actual function. And we don't even need that small of a scale to have a general idea of what it looks like. But if I plugged in, 50 different values between 0 and pi over 2, I'd have a bunch of tiny little slopes, and if I connected those together, it would look just like a sine curve. It's kind of a cool way to find a solution to a differential equation, or at least a graphical representation of it. Everybody good with that? We understand why the slope field works, how to construct it, especially for a nice simple one with just x values. Right, we didn't have to worry, all the values of x equals 0 gave us a slope of 1, right? Because the y values don't affect the derivative. Everybody good there? Any questions on that? All right, so then I'd like you guys to try to construct a slope field for this one. So I'll give you 2 or 3 minutes to plug in some x values and see what this one generally looks like. You think you can do that? All right. No one's responding. So is that a yes or is that a no? Oh, good. All right. I want you guys to do it, and then we'll see if you got it right. Ready, go. You have 2 minutes. So when x was 0, what did we get? Should have got 1, I believe, right? If x was 1, dy dx was still 1. What about when x was 2? Should have been square root of what?
3.
Square root of 3. So a little bit steeper. And as we continued, larger x values, dy dx just kept getting larger, right? X equals 3 gave us root 7, so this was even steeper. And we just kept getting steeper and steeper as we went to the right. As we went to the left with x equals -1, what did we get? That one became square root of
3.
3. So a little steeper than 1. And as we continued, -2 gave us root 7, and we were even steeper, right? And so if we were trying to sketch the curve that went through here, we might start at the origin and say, okay, we're about 1 here, and then it got steeper, and then it got steeper this way also. And we might check in between 0 and 1 just to see what was going on in between 0 and 1. We'd find out it was just a little bit less than 1, so we might have flattened out just a little bit more and then gotten steeper again in between there. But this would be good enough because they usually will give you whole number values only on the AP test. Questions on that? Are everybody good? Okay. All right. Now, nice and easy when all you're given is x values in your derivative, dy dx is cosine x, dy dx is root x squared minus x plus 1. Becomes a little more complicated when you're given both an x and a y value, right? So if I asked you to construct a slope field for this, and generally on the AP test, what they do is they'll give you a set of points that they'd like you to sketch it at. And it's generally a lot less than how many I'm putting in here right now. But that's okay. What's the easiest way to do these ones with a plus or a minus in here between two different variables? Generally, we'll just choose a value that we want dy dx to equal. So suppose I want dy dx to be 0. Well, if dy dx is 0, that tells me that y equals x. So anywhere along the line y equals x, that's this line, right? The slope should be 0. And what about when dy dx equals 1? Along what line should those be? Y equals what? If dy dx is 1, what does y equal? This should be a simple algebra question. X minus 1. So along the line x minus 1, they should all have slopes of 1. Good. And we'll probably note that as we increase dy dx, we're just getting the next line down. So a slope of 2, then a slope of 3, and a slope of 4, a slope of 5, and a slope of 6, getting steeper and steeper and steeper. And if we went the other direction, dy dx equals -1, that should be y equals x plus 1. So along, well, try to do it. Along that line, we should have slopes of -1. And then -2, and -3, just getting steeper as we go, -4, -5, -6. We end up with something that looks like that. Good or no? All right, and if I wanted to sketch the solution that went through this point, it'd curve up to here and curve out like this, something like that. Does that look good to everybody? Everybody feel all right about that? I'll assume everyone's good with that. Okay, cool. All right, last one. So I'll have you guys do this one on your own. I'm going to put out a few points here, not too many. Yes, Molly, I'll go back. So these are the points I want you to do from -2 to 2 and -3 to 3 for the y's and x values on that one. For x over 2y, Molly, there's the other one. Okay. So I'd like you guys to sketch the slope field for x over 2y on these points, these specific points. Ready, go. So obviously I didn't put a point at 0, 0 because that makes us indeterminate. Anywhere where x is 0 but y is not 0, it should be horizontal because of the slope of 0. Anywhere where y is 0 and x is not, it should be vertical. And then if we plug in just the individual points, 1 and 1 gives us a half. And then x equals 2 and y equals 1 gives us 1, and they just get steeper as we go out. And as we go up, they get a little bit less steep to begin with. And then this is just mirrored in every other quadrant. So we'll flip it down here. And a little less steep. And then same thing, it just gets mirrored over here. That's a little steep. And same thing down here, it just gets mirrored down here also. Is that what you guys got? Hopefully.
Yes.
All right. And if we sketch the solution, let's say through this point, it should just go up like, that side didn't look very good, but basically like that. And we'll note that whenever you sketch the solution, always make sure it is a function. Okay. So if I asked you to sketch the one that went through, let's say this point right here, you go up and get steeper, but you would not curve down here because that would make it not a function. You'd go until it's going to start curving back. So maybe right around the x-axis there, something like that. So you always make sure that it ends up being a function when you sketch the solution curve. Everybody good with that? All right, cool. That's as far as we're going to get today.